Okay, now we continue to solve this problem. As we just said, from this equation, let's call this one equation 1. Okay, so this is equation 1, and then this equation 2. So now we know you're going to have two unknowns, n1 and n2, right? And there's only one equation left here, that's equation 2. So we cannot solve it, and therefore that's indeterminate problem. Okay, so once we know indeterminate problem, then we know we need to use fed.cont. So we already draw the free body diagram, and then we wrote down the equation of equilibrium. So what we need will be the deformation equations. Right? So in this case, we have bar AB and bar AD, they deform, and actually also bar AC. So what we'll have will be delta 1, and that is the delta, say, AB, right, equal to N1, L1, and then EA. And then we also know delta 2, that is the delta AC, that equals to N2, L2, and the EA. And delta 3 is the same as delta 1, so we don't need that. Okay, so that's the deformation part, the D part. Right? So this is the E part, and this is now the D part. So F, E, D. Okay, now what we need will be the compatibility. Okay, so compatibility is basically the relation between all the deformations. So when you pull at this point A here, it's going to move down the distance delta. Now when this point moves down distance delta, right, how much elongation you're going to get in bar 1, delta 1, and then how much you get in bar 2, that's bar AC, right, that's delta 2. So what's the relation between delta 1 to delta 2? To illustrate that, let's show it here. Okay, let's say initially you have this point A is here. So you have this one bar here, and then the other bar here, and the other bar here, right? So when it move, it will move to a small distance down. So to make it easy to see, so let's say we make it bigger. So now you have this point move to here. Right? So when it move here, then of course this distance is actually the elongation of the second bar, and that equals to delta. So we know the delta is actually the elongation in the second bar. Now how much is the first bar elongate? You see when the point A move from A to A prime, so this bar 1, the AB, will move to this position. Okay, now how much is elongate? Will be the new length minus the initial length. So you can make a line here, project it down here. Then we say, okay, so this line here, and then this line here. Okay, so this will be the delta 1. Okay, now how are they related? Well, let's say this is the angle beta. So we know delta 1 will be equal to delta 2 times cosine beta, right? If this angle is beta. Now, what is beta? Beta is related to the original angle alpha here. Right? Now, what's the relation between alpha and beta? Well, you can say in general they may be not equal, but remember we're talking about tiny deformation, right? So this point move very small distance. Therefore, this angle alpha here is the same as the beta here. So we have alpha, beta will be equal to alpha, right? And so therefore, we actually have delta 1 will equals to delta 2 times cosine alpha. Okay. So that's the compatibility equation. All right. Now we can solve this problem by combine all these equations. Right. So we can get a solution. So you have basically now equation 2, and then the equation 3, 4 as the deformation equations, and then you have this compatibility equation. So we can solve it. Alright? Okay, so think about if you have any questions. Okay, so a quick summary about the compatibility. So we already show examples that delta 1, right, when you have two parts that are moving, delta 2. Right? They can be either equal or with opposite sign, right? They can be equal to each other, or can be one is equal, right? Or can be proportional, like when you have a rigid beam rotating, proportional. Right. Or it can be like what we just showed. There will be an angle related, right? So delta 1 equals, let's say, cosine alpha times the delta 2. Right? So that's the three common type of the compatibility equations. So the key will be for you to look at how things are moving and how each bar elongate and how they're related. So geometrically how they're related. Okay, so just quick review or further example, we can look at another situation. That is, when you have a beam like this. Okay, so here's a pin support. This point is pin support. Okay, so the beam, let's see, we have a cable here connected in the middle, and then you apply load here. Okay, now this determinate or indeterminate? Right. So we can say, oh, it's actually determinate. Why? Because when you draw a free body diagram, what you have will be this is the bar, right? So you're going to have this pin support here. So you have a reaction Ry here, and then you're going to have the load P here, and then from this bar here, going to have a reaction N1 here. Okay, now there's two unknowns, but we actually have two equations, right? Sigma Fy equals 0, sigma M equals 0. So we can actually solve it. Or in other words, you can write one equation, just quickly find out N1. That is sigma M to this point A here, this point A. So to A point equals 0. And that gives you N1 times this distance, that's half L, and then plus, actually minus this P times L, that will be 0. So that will give us N1 equals 2P immediately. So we can find out N1 with equation of equilibrium, therefore it's determinate. Right? So determinate, you find out N1 and you calculate elongation. And once you know the elongation delta 1, then you can actually calculate. So delta 1 equals to N1, right? And then times this length will be H, and then EA. And then with delta 1, you can actually calculate what's the delta at point B. So this point B here. Right? So their relation, what's their relation? So that will be actually, initially the bar is here. Now when you move to this position. So this point, how much point move? It moves this delta. Now how much this point move? It moves. This will be the delta 1. So now what's the relation between delta and delta 1? They share this angle alpha, or they're proportional, right? So delta 1 versus delta 2 will equal to the half length versus 2b, or you can say versus equal to the half L versus L, and that means so you're going to have delta 2 or equals twice the delta 1, right? So from here you can find out delta 2, and that is how much the point B move, and that is actually delta B, right? Okay, so now let's say we can change this problem a little bit. Let's say if we have this same rigid beam here, right, and we're applying load P here. Okay, so instead of, in addition to this one cable, we feel not strong enough, so we can add another cable here. Now, with this cable added, so you're going to have, this will have a reaction N1 here, and this part you're going to have N2 here. Now, you're going to have 3 unknowns because R, Y is still here, right? So you still have 2 equations, and therefore this system becomes indeterminate. Right? Okay, so you need to use fed fed.cont to solve it. All right. So now for this problem, what's the compatibility equation? It's how the different movement match each other, right? So when this bar move, it's actually show exactly the same as this one here. So this one delta 2 moves, that's be proportional to the delta 1 move, right? The elongation delta 2 and delta 1, they are related by the same equation here. So the compatibility actually will be the same as we just read there. So delta 2 will be twice the delta 1. Alright. Okay, so that's for today. Thank you.